Okay. Hello, welcome to all. In the previous lecture, we studied about mutual induction and mutual induction between two given coils. Okay. In the today's class, we will study about Maxwell's equations. You can see here the outline of today's class. Yeah, you can see here. Today we will study about the continuity equation and modification of Ampius Law and displacement current. Okay, we will be discussing about these three topics in today's lecture. Okay, first of all, let us study about this continuity equation. Okay, yeah, you are also familiar with the continuity equation in mechanics. Okay, in fluid dynamics also you have one continuity equation. Okay, here we have similar equation in electricity or electrodynamics as well. Okay, yeah, here you consider some volume in the space. Okay, suppose that there is some change in the uh, quantity of charge in that volume. Okay, right. Here, if you take the entire space, okay, then you may have the charge filled in that entire space. See, whenever we want to discuss about the conservation of charge, that conservation of charge may be two different kinds. Okay, you may require the conservation at the global scale or at the local scale. Okay, what is the meaning of global conservation of charge? That is a conservation of charge in the entire space or in the entire universe. Okay, whenever we want to discuss about the conservation of charge in a local scale, we consider a small volume in that entire space, okay, or in the entire universe. Okay, whenever you consider a small space, or you say a small volume, whenever you consider entire universe, then what is your law of conservation of charge? The total charge in the universe is constant. That is okay. Now, whenever you consider a space in the universe, a small volume in the space, then what happens is there is some possibility of charge exchange. Charge may go in or out of the volume under consideration. So, suppose that there is a change in the charge in that particular volume. Okay, then if the charge from that volume is going outside, then the decrease in that charge in that particular volume is equal to the charge crossed from that surface. Okay, the charge passed through that particular surface to the space. That means the decrease in the charge in this particular volume is equal to, okay, charge went outside of that particular volume. That means charge transfer between this volume and the space. Whatever the decrease that is resulting in the volume, that much of charge is transferred to, or that much of charge is crossing out from the surface of this particular volume. Okay, that is most obvious. Why? Because in between these two things, we assume that there is no loss of the charge. Whatever the loss of charge that is there in this volume, that must have reflected outside. That must have reflected outside. Okay. Yeah, simply this local conservation of charge gives us the continuity equation. Continuity equation in electrodynamics. Yeah, you can see here the continuity equation in electrodynamics simply emerges from this local conservation of charge principle. Okay, conservation of charge principle at the local level. Okay, now let us write the continuity equation of electrodynamics. Say now we are taking, yeah, what's our topic? Continuity equation. Yeah, to derive, in order to derive this, we are considering some volume in the space, entire space. Suppose that there is a charge q in that volume. Okay, whenever you are considering the volume, the distribution of charge within that volume is described with the volume charge density rule. So I am defining this charge field in that volume in terms of rho, because you are given the charge distribution over that volume v. Yeah. Then you may write q as simply rho dV. This is from the definition of rho, volume charge density, which we are already uh, studied in the electrostatics. Right. This is the total charge enclosed in that volume. Okay. Now, whenever the charge flows out or inside of that surface, actually the charge in motion, or the charge flow is nothing but the current. Okay. So, whenever there is a change in the charge inside that volume, then there must be a flow of a current. The direction may be inside of this volume or outside of this volume. So, this current, the total current, okay, passing through the boundary of the surface now is given by, here you are having surface now. Okay, surface distribution of current over that surface is described by surface current density J. Okay, that's why we are writing current flowing through that surface, okay, in terms of J, current density of that sheet surface. Okay, if J is the current density of that surface, okay, now we may write the current flowing out of this surface as integral J ds, integral J ds. Okay, J dot ds. I is equal to integral J dot ds. Okay, or simply I is equal to integral J ds. Okay. Now let us go for the definition of the local conservation of charge. Let us go for the local conservation of charge principle. Okay, what does this say? This says that the change in the charge, okay, the change in the charge is equal to the current. You say that means charge flowing out of that surface. Decrease in charge in that volume is equal to the current flowing out of the surface making that volume. Okay, so we have Q is equal to integral rho dV. Let us just differentiate it with respect to the time. Okay, yeah, dq by dt is equal to how much we are having? Integral d rho by dt into dv. Okay. From this equation, we are having this equation. This we use in applying the local conservation of charge principle. Okay, according to the local conservation of charge principle, this change in Q within that volume is equal to the current flow. Okay, that is, now using local conservation of charge principle, local conservation of charge principle. Okay, I will write here. This change of charge within that volume dq or dou q by dou t is equal to the current flowing, the current crossing that surface that we expressed in terms of J. Okay, we are using that expression for I in terms of J. Okay, this is minus that means current going outside of the surface, minus of J dot ds, J dot ds, right? Now, okay, you can see this on the slide as well. Yeah, we obtained this equation by using the principle of local conservation of charge. Okay, conservation of charge at the local level. Right. Here you have dq by dt is equal to minus integral J dot ds. Just now we wrote for this dq by dt from the definition of Q. What is that? Integral du by dt dv, okay, is equal to minus of integral J dot ds. See, on this side you have volume integral, on this side you have surface integral. Okay, whenever we get the same type of integrals on both sides, then simplification of the equation takes place. So in order to do that, let us convert this surface integral into volume integral, or this volume integral into surface integral. Okay, surface integral. Yeah, now I am converting this surface integral into volume integral. Okay, using Gauss law of vector analysis, yeah, it connects surface integral with the volume integral. Okay, always we prefer to convert surface into volume. Okay, yeah, then you have integral J dot ds is equal to some volume integral. You cannot write the same J here. Here you write div J, div of that vector, div, our vector is J now, d. Okay, right. Therefore, now we have this thing is equal to this thing. Okay, I'm writing here. Now on both sides you have volume integrals. See, this is okay, I'm writing it as it is, d rho by dt dv. Okay, on this side I'm writing for this integral J ds. Just now we got the expression for this in terms of volume integrals by using the Gauss law, right? I'm writing that expression here. This is now volume integral, not the surface integral. Whenever you write div for J, whenever you take divergence for J, okay, dv. Okay, right. Now, yeah, on both sides we have volume integrals. Okay, that's why in case of volume integrals, you have nothing here in between these two terms. That's why you can easily simplify such type of equations. Now you have simply dou rho by dou t is equal to minus of div j minus of div j. Okay, or you may write this as, you may write this d rho by dt plus div j is equal to 0. Whenever you take this div j to this side, you have the equation like this. Yeah. Otherwise, you may write this as d rho by dt is plus yeah, what is this div j? In vector analysis, this is del dot j. Del dot j is equal to 0. Okay? We call this equation to be the continuous equation of continuity. We call either this equation or this equation as a, this is called the equation of, this is called the equation of continuity. Yeah, we call this as the equation of continuity in electrodynamics. Yeah, I will write here the main equation here. Yeah, what is the equation of continuity? D rho or dou rho, whatever it may be, d rho by dt plus del dot j is equal to 0. We call this as the equation of continuity in electrodynamics. Okay. It is just another form of the law of conservation of charge. And the next topic of today's lecture is the modification of Ampere's law. Modification of of Ampere's law. Modification of Ampere's law. You may ask, Ampere's law is a very established law. Okay. Then what is the need to modify this Ampere's law? Modify this Ampere's law. Yeah, this motive to modify the Ampere's law is not coming from the experiment. It is coming from the theory itself. That we will see now. Experimentally, nobody challenged this Ampere's law, but from the theoretical point of view, we see some flaw in the Ampere's law or some limitedness of this Ampere's law. Theoretically, we see that it is only applicable to certain current. It is not applicable to all sorts of current. That is what the limitation we see in the Ampere's law from theoretical point of view. Okay. Yeah. First of all, let us go for the actual Ampere's law. Then we will go for the defects in that Ampere's law. Yeah, what is Ampere's law? Right here in unmodified form. According to Ampere's law, according to Ampere's law, integral v dot dl is equal to mu naught I. This is what the Ampere's law we studied in the previous lecture. Okay. Yeah. This is what the actual Ampere's law. Okay. Now, You may write this. This is in what form? This is in integral form. Yeah. In differential form, what will be the equation? If you convert it into the differential form, you have curl B is equal to mu naught J. This is differential form, mu naught J. Here you have I, here you have J. That is what the change you have to note here. Right. Now, what is curl B? In vector analysis, you know that this is just simply del cross B is equal to mu naught G. Yeah, this will be this del cross B vector will be in the direction of J. Okay, right. This is a current density. Now I is a current, J is a current, surface current density. Okay. Yeah. Now let us try to find the defect in this Ampius law. Okay. Now let us go for this differential form. Let us consider this differential form and try to take divergence on both sides of this differential form of Ampere's law. Okay. Now you just take del dot, taking divergence on both sides. Now what happens here? Del dot del cross B is equal to mu naught del dot J. Okay. You know that what is this dive of curl B? Okay, this is equal to, now you have mu naught del dot J. Okay. What is this is the general principle that divergence of curl of any vector is 0. This we know from the vector analysis. What is the meaning of that? Since curl B is equal to 0, del dot J is equal to 0. Del dot J is equal to 0. Okay. Yeah. But here we see some problem here. Yeah, this is not always true. It is only true when J refers to the steady current. Okay, because it is constant, then the differentiation will be 0. Okay. But whenever there is no need that current is always a steady current, current density is not always of the steady current. The current may be varying one also. You may also find varying currents in the universe. So, whenever you take J a representative of the variable current, then it never becomes 0. What is you are getting this from the Ampere's law, okay? But it is not always true. In case of steady current, it is okay. In case of non-steady current, it is not okay. This is what the flaw theoretically we see in the Ampere's law. So how to correct this? So as long as you take steady currents, you have magnetostatics. Whenever you want to go out of the magnetostatics, that means whenever you want to go for the time varying magnetic fields, then you have to choose time varying currents. Whenever you are choosing time varying currents, this is not correct. So beyond the magnetostatics, your Ampere's law does not work. That means this is what the flaw. Okay, whenever you want to go outside of the magnetostatics, this will not give you the correct results. Correct results. Okay, right. This we are observing from this equation. So now Maxwell wanted to modify this Ampere's law so that it is applicable everywhere. So that it is applicable everywhere. So he wanted to generalize this Ampere's law. Okay, right. Now there is another point. Just now we have seen that we have continuity equation in electrodynamics. What is that? According to the continuity equation, what is the continuity equation? Dou rho or d rho, huh? Dou rho by dou t plus del dot j is equal to 0. Del dot j is equal to 0. Yeah, see here, this is not in conformity with the continuity equation as well. Why? Because just del, according to this equation, del dot j is equal to minus of dou rho by dou t. From this continuity equation, here you are not having del dot j 0, but del dot j plus something is equal to 0. So this is not in conformity with the continuity equation as well. So we have to make it conformable to the equation of continuity as well. Okay. Yeah. For that, what you have to do? How to modify the Ampere's law? Okay. We are not doubting the Ampere's law based on any experimental fact. Okay. We are only finding the flaw with Ampere's law on theoretical grounds. Okay. So here, this is in contradiction. Del dot j is equal to 0 in contradiction with the continuity equation as well. You can see this on the slide as well. Yeah, this contradiction was fixed by Maxwell. Just now, I have seen that it should not be 0, but plus something should be 0. Okay. Here, whenever you start from the Ampere's law, finally, we have to get not del dot j plus something plus del dot j is equal to 0. So how to guess this something extra term? Something. How to get some extra term here? See here, we are having some extra divergence. That's why in all cases you are not getting 0. So in order to get 0, you have to kill that extra divergence. For that you have to add one term. One term. What is that term? Here that is emerging from dou rho by dou t. Okay, right. See, now here we use continuity equation and Gauss law of electrostatics to fix or to modify the Ampere's law. Okay, right. According to the continuity equation, what is del dot j? Okay, I will write here. According to the continuity equation, del dot j, you can see here, is equal to minus, from this equation you have dou rho by dou t, right? But whenever you use the Gauss law of electrostatics, using Gauss law of electrostatics in differential form, you have del dot E is equal to rho by epsilon. Okay, rho by epsilon naught. Del dot E is equal to. Okay. So from these two equations, so now what is your rho here? Or your rho is simply epsilon naught del dot E. From the Gauss law, your rho is this thing. Okay, substituting rho in this equation, therefore, what is your del dot J here now? Is equal to minus of, okay, yeah, minus of minus of, here you are writing epsilon naught dou by dou t of epsilon naught del dot E. Okay, now you can see here, this is del dot J is equal to minus of dou by dou t of epsilon naught del dot E. Okay, or you may write this as, or del dot J is equal to, you write minus epsilon naught outside. Okay. Next, otherwise you just write minus of del dot epsilon naught. Okay, take this dou by dou t inside of that cross product, dou E by dou t. Okay, you will write this equation in this way: dou dot epsilon naught dou E by dou t. Okay, you can see this on the slide as well. Or whenever you take this term to LHS, then what happens? It becomes del dot J plus, on this side you have minus. Whenever you bring this term to LHS, then it becomes plus. Okay, delta is outside, epsilon naught dou E by dou t is equal to 0. See, what the continuity equation is saying, not del dot J, but del dot J plus epsilon naught dou E by dou t is equal to 0. Epsilon naught dou E by dou t is equal to 0. Okay. See, so here, whenever you go for the Ampere's law, this happens when you replace J with J plus epsilon naught dou E by dou t. This will kill the extra divergence in the Ampere's law. So then what happens to your Ampere's law? So Ampere's law now is, what is that Ampere's law? Del cross B is equal to, you have mu naught J. In the place of J, now you have to write J plus dou E by dou t. Okay, now you get del dot this thing is equal to 0. Now your Ampere's law will be in conformity with the Ampere's law. Okay, what is this? This is called This is called the modified Ampere's law. See, it is applicable for both steady as non-steady current. Okay, non-steady current. See, what is the meaning of this? What is the meaning of this? Here, on this side, we have variations in the electrical field. On this side, we have magnetic field. So, according to electromagnetic induction, Faraday's law of electromagnetic induction, you have whenever you write the Faraday's law in differential form, okay, you have something different there. What is that? On one side you have electrical quantity, on the other side you have magnetic quantity. So here, there you have del cross E. There you have, according to the Faraday's law, according to the Faraday's law, del cross E is equal to minus of dou B by dou T. Minus of dou B by dou T. Del cross E is equal to minus of dou B by dou T. That means variations in the magnetic field inducing electric field. Inducing electric field. Here, according to this modified Ampere's law, on this side you have dou E by dou T instead of dou B by dou T. That means variations in the electrical field are creating or inducing the magnetic field. This is what just the converse of this Faraday's law. So, this fixing of Ampere's law, modifying the Ampere's law is very fundamental to the level that of Faraday's invention. Faraday's invention. This is what the Maxwell's invention. This is a theoretical invention. This is a practical based invention. Okay, with this, yeah, logically the theory of electromagnetic induction completes with this. Okay, right. So similar to the Faraday's law, this is also modified Ampere's law, or adding a new term is also a very fundamental discovery. Okay, later we will see the importance of this term. Yeah, this is what the modified Ampere's law. What does it conveys? It conveys that changes in the electrical field induce the magnetic field. Okay, what is the proof for this? Changing electrical field will create the magnetic field. Yeah, the proof for this came later by the Hedge, okay, who confirmed the existence of electromagnetic waves, which are the byproduct of this modification. Byproduct of this modification of the Ampere's law and subsequent Maxwell equations, which we will go later. Okay. Now, after the modification of Ampere's law, we will go for the displacement current. Who discovered this current? Maxwell, James Clerk Maxwell. Displacement current. See, again, let us go for the modified Ampere's law. According to the modified Ampere's law, what is that modified Ampere's law? On this side you have del cross B is equal to mu naught J plus epsilon naught dou E by dou T. Okay. See, now on this side the total current is of two types of current, sum of the two types of currents. Okay, this gives you the ordinary current or the conduction current. The second current, we call this as displacement current. Okay, where J gives ordinary current or conduction current, and JD is equal to epsilon naught dou E by dou T is called displacement current. Is called displacement current. Displacement current. Displacement current. Okay, right. So here the second term on the right hand side of the modified Ampius law is also a current which is having the dimensions of current only, similar to the J. That's why we call this second term as a different current called as a displacement, called as a we will call this as the displacement current. Okay, right. Yeah, now we are going to discuss in very detail about this displacement current introduced by the Michael Faraday. Okay, so now in modified Ampere's law, you have two currents. One is a conduction current or the ordinary current or the physical current. Other current is a displacement current, which is just a current equivalent but not the physical current. Actually, it is not the current, but it does the work of a current. That means it is capable of creating a magnetic field. It is able to induce the magnetic field. Okay, in this sense only we call this as a current or displacement current. This displacement current exists only when there is a time varying electric field. Time varying electric field. Why? Because in the second term you have this JD is equal to epsilon naught dou E by dou T. Dou E by dou T. Right? See, whenever there is no change in E, no variation in the electric field, then what happens? JD is equal to 0. This thing will be 0. Okay, that you have to note. So, in order to get magnetic field, only physical currents are not necessary. Just variations of electric field, okay, in free space also able to produce the magnetic field in the surrounding medium. Okay, that we have to know. Yeah, that is what the origin of electromagnetic waves. Okay. Now next, let us try to explain this displacement current in more detailed manner. Okay, what is the urgency to introduce this displacement current in the Ampere's law? Okay. Now let us consider the paradox of charging capacitor. We will first of all let us see what is the paradox in charging of the capacitor. Okay, here let us consider a capacitor which is just connected to a battery. Then what happens? Charge from the battery starts to flow inside of that capacitor. Okay, the piling up of the charge on the capacitor plate takes place. Okay, and what happens? Electric field, establishment of electric field between the plates takes place. Okay, takes place. Yeah. Now let us consider a curve for the application of the Ampere's law. Okay. Yeah. What is this? Next we are discussing about paradox of charging capacitor. Charging capacitor. Yeah, you may think that what is the paradox involved in charging of capacitor? But whenever you want to apply the Ampere's law in case of a capacitor, then actually the paradox develops. See, this is your parallel plate capacitor. you are connecting it to a battery. Okay. See what happens immediately, the flowing of charge takes place. Okay. Suppose that yeah, here this is a flat surface. This is some balloon shaped, okay, surface. Yeah, right. You're taking two surfaces S1, the other entire surface is S2. Here you have the magnetic field. Here you have the magnetic field like this. Okay. See, the current is actually coming like this, harassing this S2 surface, harassing this, what is this, S1 surface. S1 surface. Now, let us try to apply. Say this is a curve we want to consider. There are two surfaces bounded with this curve, S1 as well as S2. The edges of this S2 surface is also on this curve. The edges of S1 surface are also on the same curve. For the same curve or same contour, always you have to get the same magnetic field. Here, we are not getting the same result for the two surfaces with the same contour. That is what the paradox involved here. Right? Now, let us apply the Ampius law for surface 1. Okay? Let us take surface 1. So, according to Ampere's law, according to the Ampere's law, yeah, now let us take this S1 surface, integral B dot BL is equal to mu naught I. Why? Because say some I current is flowing into the plate. Okay, so you have I now. Why? Because I current is bounded with this surface S1. It's okay. Yeah. So this is okay for the surface 1. Whenever you go for the surface 2, okay, I will write here. Next, let us go for the surface 2. Here, applying Ampere's law will give you integral B dot dl is equal to how much here? How much current is bounded with this surface? How much current is bounded with this surface? Okay, here this surface is balloon shaped surface. See, your plate is up to here only. Okay, no current is passing into this surface or going out of this surface, but only field is passing through this surface. Right, on this side you have no electric field. Here you have E is equal to sigma by epsilon naught. On this side you have E is equal to 0 outside of the capacitor. You don't have any field either on the left or on the right. Okay, right, is equal to, actually you have no physical current passing through that surface, so you are getting 0. So this is what the paradox involves. For the same surface, for the same plate, once you are having magnetic field 0, once you are having magnetic field coming out from this thing, how it is possible? How is it possible? How to resolve this paradox? Yeah, to resolve this paradox, there must be some current equivalent to this current. Then only you have here mu naught I. So what is the origin of current in this second case? What type of current is flowing between these two plates? Okay, in this area where the S2 is located. Right? For that, yeah. Just now I wrote for the expression of E in between the two plates. What is the expression of what is the formula for E inside the capacitor? Sigma by epsilon naught. We have two plates, so sigma by 2 epsilon naught plus sigma by 2 epsilon naught. We have sigma by epsilon naught. What is the definition of sigma q by? If A is the plate area of the capacitor, then you have q by A. I am writing epsilon naught as it is. Now let us try to take the time derivative on both sides. So therefore, dou E by dou T is equal to 1 by A epsilon naught. What is this dou Q by dou T? What is dou Q by dou T? It is nothing but current. So it is just I by A epsilon naught is equal to dou E by dou T. So what is I now? What is I? Yeah, otherwise I by A is J. We write this as J by epsilon naught. Okay, therefore what is J now in this case? Epsilon naught dou E by dou T. Epsilon naught dou E by dou T. So this much of current density is assumed to prevail at the surface S2. That is due to the changes in the field E whenever the piling of the charge on the capacitor plates is taking place. These variations of electric field exist. So this variation of electric field exists through the surface S2. That is equivalent to the current called displacement current given by J or JD is equal to epsilon naught dou E by dou T. Otherwise I will write here JD is equal to epsilon naught dou E by dou T. Okay. This is a current equivalent due to the variations of electric field in between the two plates. Okay. This is what known as a displacement current. Right? Yeah. Now, so whenever you write in this case, in the second case, the current corresponding to this, okay, that is I itself. So then you have here integral B dl is equal to okay, B dl. See, whenever there is a no field, then you have 0. Whenever you have steady field, then also you have JD 0. JD 0. Okay. See, when applying the Ampius law for the S2 surface, now you have VDL is equal to I. This I due to this displacement current. Okay. In this way, you have the same magnetic field, same induced magnetic field for the two surfaces. So whenever you introduce displacement current here, then only you have the same results for B. Otherwise, you still have the paradox. So in order to avoid the paradox, we must have to assume one more current, okay, which is the equivalent of the physical current and given by epsilon naught dou E by dou T. Dou E by dou T. Okay? Right. Yeah, this is about the displacement current, physical meaning of the displacement current. Okay. Yeah. Yeah, the discovery of the displacement current is of very historical significance in the physics. This paved the way for the theory of electromagnetic waves or the Maxwell's theory of electromagnetism. So electromagnetism is logically completed with the discovery of this displacement current and fixing of the Ampius law. Okay. Right. We will stop with this. Thank you.